Before moving on to look at our other two common amplifier configurations, let's look at our adjusted common source amplifier where we add a source resistor. And so what we're going to see is that adding a source resistor R sub S is going to stabilize the Q point against changes in transistor parameters. However, we're going to do that at the cost of a reduced gain. And so that should sound very familiar because we saw the same type of thing when we were looking at our BJT circuits, specifically when we were looking at our common emitter circuit and we added an emitter resistor. So you can see page 4-16 in the notes for some more details and a refresher on that. So before we move on and look at an actual circuit, what exactly do we mean when we say it's stabilizing the Q point against changes in transistor parameters? Well, a couple different things. So one, we could be talking about one particular circuit, and as it has different operating conditions, so maybe that means different voltages and currents, or maybe the circuit is operating in a different ambient temperature, we might see changes in that parameter Gm. And so that Gm, as you recall from our previous example, we looked at a relatively simple circuit, and we found, for instance, that our voltage gain for that circuit was negative Gm R0 in parallel with Rd. And so we could also see changes in that R0 as well, depending on, again, voltage and current conditions or ambient temperature. So as we see changes in those two parameters, we're going to see fluctuations in our voltage gain. The other reason, and I think, or not reason, but other explanation of what do we mean by stabilizing our Q point, which I think is a little more applicable, is let's say you're designing some circuit and we're not just going to make one circuit, but rather we're going to send this to production and we're going to make thousands and thousands of these circuits. And so of course, every transistor that is used in all of these different circuits isn't going to have the exact same parameters. So if we have some circuit 1 over here and some circuit 2 over here with different GM values, so GM1 and GM2 and R01 and R02, and of course we have thousands of these, we wouldn't want them to behave differently just because they have slight differences due to, just normal variability in process parameters. We wouldn't want those circuits to be behaving differently because of that. So by adding this source resistor, we're going to sort of make our circuit a little more robust and a little more stable as those parameters are changing. So let's take a look here at sort of a simple circuit. So we've got our biasing network R1 and R2. We've got a coupling capacitor C sub C, some internal resistance of our input source V sub I, and we've got our RD, which we've seen before, and now the main difference is we've just added in this source resistor R sub S. So before we get into the analysis of our small signal gain, of course we need to draw our small signal equivalent circuit. So let's start by doing that. So small signal equivalent circuit. And so it might be a good idea to pause the video and try to draw this by yourself first, just to get some practice with drawing our small signal equivalent circuit. So as always, what we're going to do is we're going to start by drawing our gate, our drain, and our source terminals. So let's go ahead and label those: gate, drain, and source. Between our gate and our source, remember we don't have any connection, so we're just going to call that voltage VCS across that open circuit. Between our drain and our source, so this is an N-channel MOSFET because we have the arrow pointing out on our source. So I'm going to have our dependent current source with current flowing in the direction from D to S. It's a rough looking dependent source, but I think we can all read that hopefully. And then also between our drain and source, we have our small signal output resistance R sub naught. All right, and the source value was GM times VGS. And so that's relatively simple. That's all we need to do for our transistor. But now we need to sort of add in the external components of this circuit up here. So we can see that our source is no longer grounded, but rather we have this RS between our source and ground. So let's go ahead and add that in here. So there's our RS, and that's between our source and ground. Off of our drain, we have the resistance RD, which is going to be between the drain and signal ground. Because remember, for this small signal equivalent circuit here, we are shorting or deactivating all of our all of our DC voltage sources. So what that means is that VDD is at a signal ground. So we have RD, which is between our drain up here and our signal ground, which we said is down here at the bottom of R sub S. So this is RD, And we also know that our output voltage is defined as being across RD. So this is going to be our output voltage V0. And so I didn't draw that explicitly up here, but with a common source circuit, we know our output is defined at the drain. Okay, so now all that's left is our gate side. So we have our R1 and R2, which are parallel pass to ground. Again, that's because this VDD has become a signal ground. And then we have this coupling capacitor, which is going to behave as a short circuit for AC signals. So we're going to draw that as a short, and then just our RSI and VI. So let's add those items in. So we have our RSI and our VI. See if I can connect that a little bit better. There we go. So this is our VI, our RSI, and so that's connected between the gate and ground, and then also between the gate and ground we have that parallel combination of R1 and R2. So this is R1 parallel with R2. Okay, so here is what our small signal equivalent circuit looks like. And so let's go ahead and I'm going to define a couple terms, and we're going to use this a little bit later on as we're trying to find our equation for our small signal gain, but let me go ahead and do this now for clarity. So of course we know that this is our drain current here going into our drain, and because we've included this R0 parameter, we can see that it is going to have some dependence on our VDS, and so let's go ahead and label our VDS, of course the voltage between our drain and the source, and we see now that we have that source resistor, we no longer have that VDS is equal to V out. Instead, we have our V out is going to be equal to VDS plus this voltage at our source, Vs. And so what we can see is going into the drain, that drain current is going to be splitting into two parts. So part of it is GM VGS of this dependent source, and the other part, let's call it IX. And so that's going to be VDS over R0, so that's just the voltage there. And then at this terminal, they're combining again such that we're going to have the overall I sub D, our drain current, going through this resistor R sub S. And let's go ahead and, well, I think that's good enough for now. So we've got all of these sort of useful parameters, and so keep in mind, you can always define voltages and currents in order to help you sort of analyze a circuit. So that's a good tool to be able to have. Okay. So ultimately now we're looking for our small signal voltage gain. And so if we want to look at our small signal voltage gain, again, we're going to look at our output loop, we're going to look at our input loop, and in our output loop we're going to have something in terms of VGS, and we're going to want to relate that back to the VGS in our input loop, which we can relate to our VI, so that ultimately we get an expression for AV, which is going to be equal to V out over VI. So that's sort of our end goal. So in this case, I'm going to start on the input loop just because that's going to be a little bit easier. So we're going to start over here, and let's see what we can figure out from that. So let's do our input loop. Okay, and so on our input loop, let's say that our VI, just sort of doing a KVL, so we're going to do a KVL around this path here. So we're going to have the voltage across RS1 plus VGS plus this VS is equal to that VI voltage. Okay, so we're going to have that voltage across RS1. We can do voltage division because we just have this series combination of resistors here. So that's going to be resistor of interest, RSI, divided by RSI, plus I'm going to call that combination of R1 and R2 in parallel R Thevenin. So let me just come up here and say R Thevenin is R1 parallel R2, and of course that's multiplied by the input voltage VI, plus our next value was that VGS voltage as we went around the loop, and then finally for the VS we know that that's going to be equal to ID times RS. Okay, so I can rearrange that a little bit and solve for the VGS value, because remember ultimately we're going to have something on the output side that's going to be V out in terms of VGS. And if we can substitute for that VGS and get instead something with VI, that's going to be desirable. So if we rearrange and solve for VGS, we get that our VGS is equal to VI. And so I'm skipping over some of the algebra, but it shouldn't be too difficult to verify. If you have issues doing that, definitely let me know and I can show you a little more clearly what each of these steps are. So we have 1, so VI times the quantity of 1 minus RSI divided by RSI plus R Thevenin minus ID times RS. And so to be consistent with the notes, let me call this equation 1. Okay, so that's pretty much all the information we can get from that input loop. So now let's turn our attention to the output loop over on the right side. All right, so let's go to our output loop. Okay, and so let's start relatively simple and let's just define that V out. So of course we see we're going to have that ID is also flowing here. So our ID is going to cause some voltage drop like this across RD. So as we've seen before, of course, the polarity is opposite of what we see here for V out. So that means our gain, or rather in this case, our output voltage is just going to be negative ID times RD. So let's start there and just say that our V out is equal to negative ID times RD. And again, to be consistent with the notes, let me call that equation 2. Okay, so now let's take a closer look at this sort of Kcl, or we can write a Kcl equation here. Let's look at this junction where our drain current is splitting into GM, VGS, and our Ix value. So we have ID coming in and then those two other currents going out. So we can say from Kcl, what we have is ID is equal to, and let me move this down here so I have a little more space. So our ID is going to be equal to what we called Ix plus GM times VGS. And so this is going to be equal to, as we said before, the Ix is going to be VDS over R naught plus GM times VGS. And so we can rearrange this a little bit because we can substitute for our VDS. So we kind of said this in passing as well, but we can say from KVL our VDS is equal to V naught minus Vs. And our Vs is, of course, ID times Rs. So sort of doing all of that in one sort of calculation, let's adjust that. We can say this is really V out minus ID times Rs. And so we divide that by R naught plus GM VGS. And so let me pause here for a second and say this analysis is a little more complicated than what you're seeing in the book because I've chosen not to neglect this small signal output resistance. If that wasn't there, this would be a lot simpler. However, we're going to get a more general expression, and then from there, of course, we can simplify for the case of if that R naught is infinity. Okay, so continuing on with what can sometimes be pretty messy, let's take this equation. So now we see we have an ID on the left side, and we also have an ID over here. So let's sort of clean that up and solve this for ID. So if we solve that for ID, just sort of again combining those two ID equations, we're going to get that ID is equal to R naught divided by R naught plus Rs times, and then we have V out divided by R naught plus GM times VGS. And let's call this equation 3. Okay, so now we've sort of got all of the information, so we can get more equations from this circuit, but it's all going to be redundant information. We've kind of covered all of our KCL, all of our KVL loops. So now what we want to do is sort of combine and play around with these equations 1, 2, 3. So we have all the information, we just need to sort of massage it into the form that we're looking for, which again is of course ultimately this AV expression here. So let's start by substituting expression 3 for our drain current into expression 2, as you see on the top of the screen there. So let's say we're going to substitute we're going to substitute 3 into 2. And after we do that, we're going to solve for our V out. And so skipping over some of the steps, but again, if you want to see more details on that, what we're going to end up getting is that our V out is equal to negative RD times R naught GM VGS, all of that divided by R naught plus RS plus RD. So a relatively simple expression for our output voltage. And so let's call this equation 4. And so again, this wasn't a new equation from the circuit, we've just sort of combined some of those previous equations to get this. So now what we're going to do is we're going to rearrange expression 2, and we're going to substitute that into expression 1. So let's go ahead and write that out. So we're going to solve equation 2 for ID. So right now it's in the form of V out equals negative ID RD. So we're going to rearrange that and solve for ID. And once we do that, we're going to then substitute that ID expression into equation 1. So substitute into equation 1. So we've got it's some expression here in terms of ID, so we'll solve this for ID, and then we're going to come up here to equation 1 and we're going to plug that in for our ID here. After we do that, we're going to take that modified form of I1, or sorry, not I1, of equation 1. So take, or not, let's not say take, let's just say we're going to substitute modified equation 1 into our equation 4. So ultimately then we're going to have some equation for VGS, which we've modified by taking this ID and putting it here. And what we're going to get then is we're going to take that VGS value and we're going to plug it in for this VGS here. And so what we're going to see is ultimately that's going to have all of those undesirable variables cancel out. So again, sort of glossing over a lot of the steps, what we end up getting is that our Vout, so this is Vout times R0 plus RS plus RD plus R0 GM RS divided by R0 plus RS plus RD, and that's going to be equal to Vn times, and we're going to have a couple values over here, so we're going to have negative RD times R0 GM divided by R0 plus RS plus RD, and that is multiplied by our sort of voltage division ratio, R Thevenin, times R divided by RSI plus R Thevenin. So it's actually been modified a little bit. Again, that just sort of comes out in the algebra. And so what we can see is we have a couple terms canceling out. So we've got this canceling out over here with this. And so now what we can do is we can just divide both sides through by that Vn, and we're going to get our desired AV, which again is equal to Vout over Vn. And so adjusting this form a little bit to make it more simple to see what happens when our R0 goes to infinity, we can say that this is going to be negative R Thevenin divided by RSI plus R Thevenin. And again, remember R Thevenin is just R1 parallel R2. And here's where I'm sort of adjusting the form a little bit. We can say this is equal to GM times RD in the numerator. And in the denominator, we have 1 plus RS divided by R0 plus RD divided by R0 plus GM times RS. Okay, so that was a lot of work, but here is our relatively general equation. But again, keep in mind, this is for this particular circuit that we're considering here. So if we change this circuit structure, that's going to ultimately change this gain equation. So be familiar with how to slightly adjust the gain equation based on slight adjustments to the circuit. Of course, in an exam situation, I'm not going to expect you to go through all of that derivation process to get to some gain equation or output resistance as we see here. So a couple other things we want to do. Let's say we then want to simplify this and we want to talk about the ideal case. So in our ideal case, our small signal output resistance is going to be infinite, and the input resistance associated with our source, RSI, is going to be 0. And so looking at this equation up here, we can see with our RSI equal to 0, this first term is just going to go to 1. So this whole term here is going to go to 1. And with our R0 being 0, or sorry, infinity rather, we're going to have infinity here, and that means those two terms are going to be going to 0. So this will be 0, this will be 0. And so we can write for this ideal case then, our voltage gain is going to be equal to negative GMRD divided by 1 plus GMRS. And so if we compare that to the previous equation, so it wasn't for the exact same circuit configuration, but without the RS, and I think it was just a single drain resistor biasing, we didn't have any biasing network at the gate, we found that our AV, and so I'd written this above as well, was negative GM R0 parallel RD. And so what we can see is that in this equation we have a lot less dependence on that GM. So less dependence on our GM parameter, in other words, our transistor parameter. However, what we can also notice from that is because we have that GM RS term in the denominator, now we're going to be reducing the gain. So as we said, that's going to come at the cost of a reduced gain. Just like we saw with our emitter, our common emitter circuit with our BJTs, one thing that we can do is we can implement a bypass capacitor. So bypass. So if we have a bypass capacitor, we can come up here and we can have a capacitor that bypasses all or part of our RS. So this could be our C sub S. And what that does is our RS is going to be present for the DC analysis, so it's still giving us that stability for our Q point, but it's not going to be showing up for our AC analysis. So in this case, we wouldn't necessarily want to bypass all of it because then we revert to sort of that more simple equation, but we could, for instance, split that RS value into two parts and bypass one of the two parts. So we can kind of sort of try to find a middle ground between Q point stability and not reducing our gain too much. And what we're going to see in a later course is that it's actually even better to just bias these amplifier networks using a current source. And so you can look a little bit more on page 225, so that's discussed, but again, this is something we'll talk about in detail in a later class. So current source biasing is typically what's going to be done, particularly if these amplifiers are going to be used on any type of IC. So current source biasing.